Guys, I hope I find you well. Guys, if you want to receive anytime, anywhere, the videos that I upload on this channel of yours, remember there's a notification button. If you hit it, wherever I upload a video, you'll be notified. Also, guys, if you're finding value from the videos I'm uploading on this channel of yours, you want me to continue to upload and upload, subscribe, hit that button. It's otherwise, enjoy, and I'll keep on uploading and uploading. Electrical engineering technology, telecommunication engineering, networking, computers, you name it. It's otherwise, let's enjoy the next video, BJT. Guys, welcome to the 14th video on Electronics 1, and this is Bipolar Junction Transistor, BJT. On BJT, we'll be talking about two junctions, not one junction, which we were doing on or in our previous video or presentations. This is a topic which I always say separates boys from men, in that we have got two junctions that we'll be talking about, reverse and forward biasing of the two. I hope, guys, you enjoyed the last video or presentation that I gave you on the Zener diode. It is a very important device in electronics. My name is Moshe Marufu, and guys, I hope you are enjoying what I am giving you on this favorite channel of yours. If you are doing so, don't forget to subscribe after being blessed with the stuff that you need. Let us go. Under objectives, guys, by the end of this video or presentation, you must be able to differentiate an NPN from a PNP transistor. You must also be able to name and identify the three terminals of the BJT from the schematic symbol, and also from, or using rather, a multimeter. Then you must be able to explain with the aid of diagrams the construction of BJT, both NPN and PNP. Then you must be able to describe the characteristics of a BJT. BJT simply means bipolar junction transistor in cutoff, saturation, and active regions of operation. Then you must be able to explain the concept that a transistor is a current controlled device, and state the relationship of the three currents: emitter current, collector current, and base current. Then last but not least, you must be able to define alpha DC and beta DC of a transistor and use typical values in transistor calculations. A transistor is found in most modern electronic systems and working or carrying out different functions. It is a three-terminal device. We know BJT is a two-terminal device, and the output of the BJT, whether it is current, voltage, or power, it is controlled by the input current. Its important function we are going to discuss in this course is as an amplifier, in that it increases the input signal so that the output is greater than the input signal. Its other important function that we are also going to discuss in this course is it can be used for high-speed switching, since it can do that at a rate of several billions of times per second. Guys, there are two types of transistors, BJT and FET. BJT makes use of two charge carriers, majority and minority charge carriers, while a FET makes use of either majority charge carriers or minority charge carriers, and in this case it makes use of majority charge carriers. What I wanted to emphasize was it is a unipolar. When a person refers to, or when a person mentions the word a transistor, it is assumed that he will be talking about BJT, since FET is simply referred to as FET. And we've got two types of BJTs. BJT simply stands for bipolar junction transistors, NPN and PNP transistors. We are going. As I said, a transistor has got three terminals or three legs. That's the base, collector, and emitter, and it can operate in 3 regions. It has got 3 connection configurations: common base, common emitter, and common collector. Don't worry, we'll cover what that means. It can be used as a voltage as well as current amplifier. You know voltage and current from your EET course. The word transistor comes from 2 words joined together: transfer and resistor. And what we mean when we are saying transfer resistor? We are simply saying the input signal is transferred from a lower resistance base emitter or emitter-based junction to a high-resistance base collector junction. It is important to also know that there are 2 types of transistors. One is unipolar, the other one is bipolar. Unipolar junction transistor refers to a field effect transistor, or field effect transistor make use of one charge carriers, whereas bipolar junction transistor, BJT in short, makes use of 2 charge carriers. It is explained, and as I said, we are going to discuss 2 types of BJTs in this presentation: NPN and PNP transistors. First things first, we want to know how a BJT transistor or a BJT is constructed. It has got 3 terminals, as you can see. That this is in the construction of an NPN transistor. NPN, as you can see, this is called the collector, this is called the base, and this is called the emitter. And there are 2 junctions. This is one junction, and this is another junction. Also, as you can see, the base is sandwiched between 2 N-type materials. In terms of doping, this is the material that is most doped, followed by the collector, and the base is the least doped. Even in terms of size, this is the smallest. Guys must be able to draw and to describe the construction of both NPN and PNP. Emitter emits electrons because it is heavily doped. The collector collects electrons. Then the base is the controlling element. As I said, two important characteristics of a base: it is slightly doped, and also it is thin. And its function, it controls the flow of current. How does it do that? Due to recombination. Go through the stuff. It is very important. NPN and PNP construction and their schematic symbols. Guys, I've emphasized that when you are drawing circuit diagrams, we use schematic symbols, and this is a schematic symbol for a NPN transistor and also a schematic symbol for a PNP transistor. The arrow is pointing out, so it's not pointing in, and is from the base to the emitter. So this is an NPN transistor. The arrow is pointing in and is towards the base. So this is a PNP transistor. You must label the terminals or the legs correctly. Then the NPN transistor is got a base sandwiched between, the base is P-type and is sandwiched between 2 N-type materials: collector, base, emitter. These 2 are opposite each other. Even on the schematic symbols, they are opposite each other. The terminal with the lead is the emitter, then the opposite end is the collector, and in between is the base. The same applies to you. The terminal opposite the emitter is the collector, and the material in between is the base. So you must be able to draw the construction diagrams for the 2, and also to represent the 2 using schematic symbols. In its explanation of the previous slide, and as I said, the arrow identifies the component terminals, in that the terminal with the arrow is always the emitter, and the opposite terminal becomes the collector, and in between is the base. The arrow always points towards the N-type material. If the arrow points towards the base, the transistor is a PNP. If it is away from the base, it is an NPN. Then the arrow shows the movement of conventional flow of the emitter current from positive to negative, and we know that electron flow is the opposite. Then a BJT, as seen, it has got two PN junctions, base emitter and collector base, and for it to operate as an amplifier, emitter base junction must be forward biased and the collector base junction must be reverse biased. The operation of unbiased BJT, and as you can see, no voltage source is connected. We have simply put the three materials together, and after a while the two depletion regions are going to form. And please take note that it is spread more into the base than into the collector or into the emitter, and there are two junctions there, the depletion region at the emitter junction and also the depletion region at the collector junction. It is spread more into the base, it is spread more into the base, and this is the polarity for an NPN transistor. For a PNP, it will be opposite. So the width of the depletion region is not the same on both sides of the junction. Why? Because electrons are going to spread more into the base because they are looking for holes to recombine. Electrons are going to spread more into the base because they are looking for holes to combine, and holes are scarce in the p-type material because it is slightly doped. This graph is showing the potential between the from this point to this point, and it is decreasing towards this point, and it is also decreasing towards this point, and it is the same on this junction as well as on this junction. So it simply shows the dropping in potential as you move away from this point onto this point, and from this point onto this point, and we are calling this the barrier voltage. Note the change in polarity of VB for a PNP transistor when compared to the NPN transistor. This time we've got the positive terminals instead of the negative terminals towards the base, and also positive terminal towards the base. But as usual, because the base is slightly doped despite the type of material, the depletion layer is spread more into the base than into the collector or emitter for the same reason as in NPN. But another change here, the potential is decreasing from this point onto this point, hence this shape, and this is the barrier voltage as you can see. So that's insofar as PNP, unbiased PNP BJT is concerned. Transistor operating regions, also referred to as modes, and it was highlighted that a transistor can operate in 4 regions, but we are going to discuss in detail 3 regions and the top 3 ones according to our table. And these regions are defined depending on the bias between the 2 junctions, emitter junction and collector junction. And we are saying when emitter junction or base emitter junction is reverse biased and the base collector or collector junction is reverse biased, we say the transistor is operating in the cut-off mode or region, and that typical connection is used when the transistor is acting as a switch. Then the other mode is called the active mode, and this is where our subwoofers operate on. The base emitter junction is forward biased and the base emitter junction is reverse biased, and the typical application is BJT as an amplifier. Then when the 2 junctions are forward biased, we call that the saturation mode or saturation region. And where do we use this type of configuration? When the BJT is operating as a switch. So a switch can operate in 2 modes, at cutoff and also at saturation. Then this mode, the inverse region or inverse mode, we are not going to discuss it in detail, but it is used in digital circuits, and the emitter junction is reverse biased and the collector junction is forward biased. We are going to look at the connections of these in the coming slide. Let's go. Circuit diagram, a representation of transistors operating in the 4 regions. We are simply following the previous slide where the operating regions were defined by the bias at the emitter junction as well as at the collector junction. And we said for a transistor to work in the active region, the base emitter junction must be forward biased, and the collector base junction must be reverse biased as shown. So I want to show you whether this is correct. We've got the emitter base or the base emitter. This is the p-type material, since this is an NPN transistor and it is connected to the positive. So we are going to see majority charge carriers flowing. Hence, we can safely say the base emitter junction is forward biased. The base collector junction must be reverse biased, and as you can see, the n-type material is connected to the positive terminal. So majority charge carriers are not going to flow. So we can safely say the base collector junction is reverse biased. Let's have a look at the transistor operating in the saturation region, NPN transistor. This is NPN, and please take note that this polarity is wrong. I made an error there, but the cell is the bias voltage is connected correctly. The negative is connected to the n-type, the positive to the p-type. So we can safely say the base emitter junction is forward biased, and also the base collector junction is also forward biased for the transistor to operate in the saturation region. The negative terminal is connected to the n-type material, hence majority charge carriers are going to flow. So forward bias and forward bias to the two junctions results in the transistor operating in the saturation region. The cutoff, the transistor's two junctions must be reverse biased. The positive terminal of emitter base voltage is connected to the n-type material, so this junction is going to be reverse biased. The base collector junction is reverse biased as well. Why? Because the p-type, the positive terminal of the collector to base voltage is connected to the n-type material, so electrons are going to be attracted to this terminal. So we can safely say this transistor is correctly biased for it to operate in the cutoff region. For the inverted region, the positive terminal is connected to the n-type material, so this junction is reverse biased. The negative is connected to the n-type material, so this junction is forward biased. So we can safely say this is a correct connection for transistor operating in the transistor to operate in the four regions. More on BJT operating regions. When the transistor is fully off, we say it is operating in the cutoff region. When fully on, it is operating in the saturation region. When in between, we say it is operating in the active region. And the fourth operating region, which we are not going to discuss in this presentation, is the inverse active region. For a transistor to operate as an amplifier, it must be operated in the active region. Please take note. Let me repeat, the base emitter junction is forward biased by the DC source, which is VEE in our case, according to the previous slide. And when forward biased, it means the depletion region width decreases. The base to collector junction is reverse biased, thus widening the depletion region. When we forward bias, we cause majority charge carriers to flow, and when we reverse biased, we cause minority charge carriers to flow. In the base, we have got recombination because of the material that is different from both the collector and the emitter. Because the base is lightly doped, there's going to be little recombination with the holes or with electrons, depending whether the transistor is PNP or PNP. The current due to recombination is called base current IB. But since it is lightly doped, it means electrons for an NPN transistor from the emitter, most of them are going to cross the base emitter junction and the base collector junction to become collector current due to attraction by the positive terminal of VCC, and this constitutes collector current. Because it is reverse biased, it means that we are going to have majority charge carriers as well, meaning our collector current is due to minority charge carriers as well as a current due to majority charge carriers. the relationship between the three currents of the BJT. Emitter current is equal to collector current IC plus base current IB. So IE, that E stands for emitter, and we know the symbol for current is capital letter I. So IE emitter current is equal to collector current plus base current IB. And we know that because of that equation, emitter current is greater than collector current. We also know that because the base is slightly doped, current due to recombination is therefore very small. Hence, we can make this assumption that emitter current is approximately equal to the collector current. And I think we are aware of Kirchhoff's current law as shown by our previous slides. And as we saw, collector-based junction is reverse biased, meaning there are majority charge carriers as well as minority charge carriers. Hence, BJT, hence the name BJT bipolar, because of those two charge carriers. Minority charge carriers or current due to minority charge carriers flow is also known as leakage current. Please take note of that commonly used phrase. Guys, take note that my explanation for NPN also holds for PNP, except that in PNP, majority charge carriers are holes, whereas in NPN, they are electrons. But the forward biasing and the reverse biasing and the effect remains the same. So instead of talking of electron being majority charge carriers, we say most holes from the emitter, which is P-type, they cross the base into the base and the base collector junction into the collector region to reach the negative terminal of the external voltage source, which is our VCC. That's simple. Please take note of the inclusion of the current limiting resistor RC and RE. RE stands for emitter resistor and IC stands for and RC stands for collector resistor. The current flowing through this resistor is called collector current IC, and the current flowing through the emitter resistor is called IE, standing for emitter current. Please take note of the polarity of VEE for forward biasing, and please take note that these directions are showing the conventional flow of current and not the electron flow of current. Please also take note that the barrier voltage at the base emitter junction is less than the barrier voltage at the collector to base junction. Please take note of this. This shows the size of the voltage as you move from this point to this point. Then for a PNP, it becomes opposite. And please take note that the spreading of the depletion regions around each junction remains the same. And also, we still have RE, but the direction of flow of conventional current has changed. In this case, it's now getting into the emitter from VEE, as well as the base current and the collector current are flowing out of the transistor. Hence, IE is equals to IB plus IC. Please take note of the polarity of the supply voltages, VCC and VEE, for PNP as well as for NPN. Because we've introduced the supply voltages as well as the terminal voltages and the junction voltages, it is important that we look at transistor voltages because we'll need this when we do BJT biasing. And we are saying VCC and VBB and also VEE are supply voltages. How do you detect that? When the subscripts are the same, those are referred to as supply voltages. But when we only have got one subscript, we call them transistor terminal voltages, and they are measured with respect to the ground. When we've got two different subscripts, these are known as junction voltages, and they are measured between the two terminals of a BJT. Let's see in the coming slides what we mean by these transistor voltages. A diagram or a picture is worth 1,000 words, as you can see. This is our VCC and this is our VBB. And as you can see, this positive terminal is going to forward bias the base emitter junction, and this negative terminal is going to reverse bias the collector base junction, and these two are what we call the supply voltages. And please take note, the subscript are the cell, and the voltage can be VCC, VBB, or VEE. So the flow of current will be in this way, because this is the current going out of the transistor according to the schematic symbol. It means that if you follow the conventional flow current, we are going to have current flowing in this direction as well as in this direction. Then output current IE is equals to base current plus collector current. That's interesting. We are now going to discuss what we call transistor terminal voltages. These are measured with respect to the ground, and this is our ground, our ground, our ground, our ground, our ground, our ground. The ground is also acting as the negative terminal, as you can see. And we are saying this is the collector. So the voltage from the collector to ground or to the negative terminal, we call it collector voltage. The voltage at the emitter with respect to the ground or the negative terminal, we call it the emitter voltage. Then the voltage at the base measured with respect to the ground or negative terminal is called the base voltage, VB. So you can see that this is a positive voltage, this is a positive voltage, and this is a positive voltage, and this applies to an NPN transistor. For a PNP transistor, this will be negative there, positive there, negative there, positive there. So this is showing us where terminal voltages are, or what terminal voltages are. Transistor junction voltages. These are voltage measured between two terminals, between collector and emitter. This is the collector, this is the emitter. Between the collector and the base, and between base and emitter. This is our base and this is our emitter. And please take note of the polarity there. When for a PNP transistor, the polarity will be opposite. So that is it insofar as transistor junction voltages is concerned. In other words, it is important to know these voltages, because sometimes when there is a leakage of current between these two terminals, and when it is very, very low, it will cause the transistor to conduct heavily, resulting in it hotting up. That table is a summary of the three voltages we have been discussing, and we said when the subscripts are the same, these are the supply voltages, and when we only have got one subscript, these are terminal voltages, and when we have two different subscripts, these are known as junction voltages. So CC, a collector, base, emitter, these are supply voltages because the subscripts are the same. Collector, base, emitter, these are terminal voltages. Collector, emitter, collector, base, these are junction voltages. Guys, you must know these voltages because it will be of great assistance or help to you when we discuss bias circuits for BJTs. A relationship of the three transistor currents, and this is the equation. I stands for current, so this emitter current is equal to collector current plus base current, and this can be deduced using Kirchhoff's current law from the three schematic symbols with currents labeled. This is the collector, so the current flowing in the collector is called collector current. This is the base, so the current flowing in the base is called base current, and this is the emitter, and the current flowing through it is called the emitter current. As you can see, these are flowing towards the transistor, so they must be equal to the current flowing away from the or out of the transistor rather. So guys, you must be able to draw and to show the direction as well as to label the currents. Please take note of the difference between the direction of the currents for a PNP transistor. This is our emitter because that's where the arrow is, and it is flowing towards the base, so it must be equal to these two currents flowing away or out of the PNP transistor. Getting interesting and hot by each slide. I hope you are enjoying. That slide is simply showing the direction of current flow as well as the size of a current. As you can see, there is very little base current due to low recombination. You can see that we've got 3 holes. So it means our base current is going to be very low. Hence you can see where the pointer is. As you can see, there is high emitter current because the base is highly doped. So our emitter current is going to, most of the emitter current is going to reach the collector. Why? Because only very little current is going to flow through the base due to recombination. And as stated, the collector is very positive and it attracts the electrons. Why positive? Because of this polarity there. The emitter is very rich with electrons. Why? Because it is heavily doped. The emitter is very poor with holes. Hence, there is little recombination. As you can see, base current is flowing this direction. Collector current is flowing this direction. So, emitter current is flowing in this direction towards the transistor. By the end of this presentation, there was, if you remember your objectives, we are required to be able to define beta as well as alpha. Beta is also referred to as beta DC, and this is how it is obtained given collector current and base current. It is also referred to in H parameters of a transistor as HFE, but the equation remains the same, and it is defined as the ratio of the DC collector current to the DC base current. Please take note that if you make collector current the subject of the formula, it becomes collector current is equal to beta IB, which is beta times base current. So given base current and beta, you may be asked to find collector current. If we go to our original equation, which reads emitter current is equal to collector current plus base current, we have replaced the collector current by beta IB according to the formula for beta is equal to collector current over IB. If you factor out base current, it becomes base current in brackets beta plus 1, which means that if you've got beta and IB, you can find emitter current. Clear? And it is interesting. BJT worked problems. Number 1, determine the emitter current in a transistor when the base current is 1 milliamp and the collector current is 15 milliamps. We know that emitter current is equal to collector current plus base current. So you simply add the 2 and you get 151 milliamps. Guys, you must be able to convert from milliamps to amps because some examiners can mix these 2 units. So when you add them, you must make sure that they are in the same unit. Number 2, find beta of a transistor with a base current of this and a collector current of this. Guys, beta is equal to collector current divided by base current. So like this, you must guess this value 200. This is correct because we said the range is from 10 to 600. If you find a number outside that range, then there's something wrong with your calculation. Please don't forget to make take prefixes such as milli and micro into account when using the beta equation. Like in this case, the emphasis is that you must be able to use your scientific calculator and to punch correctly. For example, in this case, collector current is 5 milliamps, but base current is equal to 25 microamps. So if you punch correctly, you must get a value of 200. And please take note, this has no units. Guys, we've come to the end of BJT presentation, but it's after solving this one. Find collector currents in a transistor circuit with a beta of 40 and a base current of 85 milliamps. We use our formula. Collector current is equal to beta IB. You multiply the 3, you get 3.4 amps. If you don't get this on your calculator, there's something wrong with your punching. Then the last thing in this presentation, and according to our objectives, is alpha, and this is also referred to as large signal current gain of a transistor. It is the ratio of collector current, this time not to base current but to emitter current. Guys, you must be able to make IC the subject of the formula so that you get alpha IE. We are going to revisit in more detail alpha and beta in our next video presentation on BJT connection configurations, where we'll be looking at common base, common emitter, and common collector. Until then, guys, bye. Take care of yourself, especially during this COVID time error. If you have enjoyed this video, guys, don't forget to subscribe, because you are the ones who make this channel tick. Motion Marufu.